Hello, welcome to Mystery Science. Tonight we're going to be talking about space. As usual, we're going to be using the Pearson EdExcel A-Level Physics textbook. I'm looking at EdExcel A-Level Physics 2 because this is part of the Year 13 content. And the space section is topic 12 in that textbook. There'll be links below to my affiliate account for Amazon if you want to purchase a textbook and follow along yourself. Chapter 1 of this topic is called Starshine. I'm not sure why that looks like an M, but it is an N. It is Starshine. Right, so if we think about the universe, we think about the stars around us, and the stars around us are so mind-bogglingly far away that we don't really have a lot of information about them. We can't just go up to them and start studying them like we can our own star. Even that is physically very difficult. So imagine trying to study the stars of the universe billions of light years away. Even the closest star to us is so far away it would take years for light even to travel back to us. So the only thing we can information we can gather about them is in fact the light that they transmit to us, the electromagnetic radiation that reaches us here on the Earth. So this tiny amount of information is enough though for us to deduce a great deal about these stars. We're able to deduce temperature, the chemical composition, the speed that they're moving either towards us or away from us, their approximate age and size. And in this lesson today, we're going to have a look at just a little glimpse of how astrophysicists are able to use the electromagnetic spectrum to deduce all of this information. We're then able to classify them by colour and size. Things like white dwarf, red giant, a supergiant, blue hypergiants, etc. So this topic is really about unlocking just a little glimpse of the secrets of the universe. So this is a still image of a galaxy called NGC 290. Now, this is quite a good image for us to kind of look at and see if we can gauge which of these is the brightest star. Would you be able to tell, looking at this picture, which one is the brightest, which one is the largest, which one is the closest to us, and which one is the hottest? Now, just looking at this light visually, we have a problem. We can only really detect 5 or 6 different levels of brightness. We can cluster them into kind of like the small little specks and the big blue glares and then the red glares and the different sizes, but really visually we're not able to pick apart much information from this image. However, that's what astrophysicists are actually doing. We're taking a range of the electromagnetic spectrum that's being transmitted from that star to our planet, and we're using that to be able to determine so much information about the star itself. And I'm going to talk to you about 2 different laws, the Stefan-Boltzmann law and Wien's law, that will help us determine the size and the temperature of the stars that we are looking at. So let's first start with the Stefan-Boltzmann law. Now, first we have to define a term called luminosity. Now, this is the total radiated power output across the entire electromagnetic spectrum from one thing. We don't just talk about brightness when it comes to stars. We have to talk about the whole transmission of the entire electromagnetic spectrum. So we're talking radio waves all the way up to the gamma rays. The visible light obviously is just a small section of this entire spectrum. A blackbody radiator is a perfect emitter which gives off perfect amounts of energy across the entire electromagnetic spectrum. So you would have an uninterrupted line of energy being transmitted from the object throughout the whole of the electromagnetic spectrum. And we'll understand why that's an important distinction later through the topic. So the Stefan-Boltzmann law relates the luminosity of the star to its surface area and its absolute temperature. We are able to determine how big a star is and how hot it is based on the power transmitted from the star. And we use this using the following equation, and that's that luminosity is equal to sigma, which is the Stefan-Boltzmann constant, multiplied by the surface area of the spherical star, multiplied by the fourth power of the temperature. So sigma is the Stefan-Boltzmann constant, and that's 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the minus 4. So this graph here shows perfect black-body radiation. If we have a star that is at 6,000 Kelvin, we could follow the red line. You can see there's complete total emission. There's a smooth curve with a peak with a wavelength at lambda 3. We'll talk about these peaks and these wavelengths in a moment. But there is no missing energy. All of the energy is there, all the way from the blue end of the spectrum, back to the long end of the spectrum. And as you can see, despite the colors of the lines, the larger the star, the hotter the star, the bluer the bluer the spectrum that comes from it. So let's use this information then to do some calculations. So if we use Stefan-Boltzmann law, we can find out the luminosity of the sun, given that its radius is about 7 times 10 to the 8 meters, and it's got a temperature of 5,800 Kelvin. So we know that the luminosity is given by sigma times surface area multiplied by fourth power of temperature, and that the surface area of the sphere is given as 4 pi r squared. So we can just plug these numbers in now. We know that the Stefan-Boltzmann constant, 5.67 times 10 to the minus 8, multiplied by 4 pi times 7 times 10 to the 8 squared, multiplied by 5,800 to the power of 4. If we put all those numbers in, we end up with a luminosity for the sun of 3.95 times 10 to the 26 watts. That's a lot of power, which is what we expect given that the Earth is the energy source for the planet and the whole solar system. So let's now imagine that we have a star which is twice the radius of the sun, but it's the same luminosity. So we can now calculate the surface temperature of a star which is twice the size but has the same luminosity as the sun. So we know then the luminosity of the sun and our mysterious star is 3.95 times 10 to the 26 watts, and that the surface area of our new star, 4 pi r squared, is given as 2.46 times 10 to the 19. And so we just rearrange the equation now. The temperature is the fourth root of the luminosity divided by the Stefan-Boltzmann constant multiplied by the area. And that gives us this. Apologies, my powers seem to have gone a little bit odd here, but this is 3.95 times 10 to the power of 26 divided by 5.67 times 10 to the minus 8 times 2.46 times 10 to the power of 19, all in the fourth root. And this gives us a temperature of 4,100 Kelvin. So this shows us that a star that's twice the size of the sun but has the same luminosity actually has a lower temperature. So we can have different stars of completely different sizes at different temperatures but have the same brightness in the sky. So how do we determine what the actual temperature of the stars are? And this is where we go back to that curve with the blackbody radiation, and we use Wien's law or Wien's law to calculate the luminosity of a star. We've got to know that its temperature. We've just used the Stefan-Boltzmann constant, but how can we determine that? Using just the electromagnetic radiation. And this comes into Wien's law. We examine the entire spectrum radiated by the star, and I'll show you an example of this in a second. The wavelengths of the spectrum are emitted with completely different intensities. I showed you that graph earlier where we had 3 different temperatures of radiation, and they had different peaks of wavelength. So here's one. Here's an actual spectrum of light emitted by the sun. Now you will see that it starts from the blue end of the spectrum, from the kind of gamma rays, and then increases in intensity right up to that kind of light blue peak there, and then comes back down through the red end of the spectrum all the way down through the radio waves. Now you'll notice these kind of troughs in this graph. Now that is going to become very important later on in the topic, but we're not going to really touch on that now. Right now we're just going to focus on the fact that we have this peak at that wavelength round about 450 there, and we'll talk about that in a moment. So what can we do with this? Well, now we can determine the relationship between the peak wavelength, and this is Wien's law or Wien's law. And there's the temperature multiplied by this maximum wavelength, that peak wavelength, always, when multiplied together, gives 2.898 times 10 to the minus 3 meters Kelvin. So if we look at the spectrum of light from Betelgeuse, and that's a large star in the constellation of Orion, its peak wavelength is 935 nanometers. So what is the surface temperature of Betelgeuse? So now we just take this equation, temperature multiplied by peak wavelength is equal to 2.898 times 10 to the minus 3, and we simply divide that constant by the wavelength, so 935 nanometers, and that simply gives us a temperature of 3100 Kelvin. It's quite simple. So with that, I'm going to leave you with these 4 questions. And don't worry, I'm going to film the solution to these questions, and I'm going to upload them immediately after uploading this. I am, however, going to set it a day later, so there'll be no cheating. So here we go. Here are your questions. The first one, quite simply, what is the luminosity of the star Sirius? It's got a surface temperature of 12,000 Kelvin and a diameter of 2,220,000 kilometers. Question 2. The sun's surface temperature has been measured as being 5,800 Kelvin. Please calculate the peak wavelength of the solar spectrum. But the peak wavelength from the sun is in fact measured on Earth as being about 470 nanometers. You're not going to get that as your answer to question A. The question is, why not? Why is it different? And then finally, calculate the peak wavelength output you'd expect from Bellatrix if its surface temperature is 21,500 Kelvin. And then lastly, we have a graph here. Calculate the temperatures of Canopus and Rigel. Canopus is that blue line and Rigel is the red one. So try and determine what the wavelengths are from this graph and then calculate the temperatures. Right, thank you very much. That was a very short introduction to the space topic and the first chapter, which is Starshine. I'm going to be doing the next few chapters over the next couple of weeks. What I probably will do is do 1 chapter per video. So again, these little short videos. Please do leave a comment in the comment section below Let me know how you're finding these videos. Do you want me to try something different? Would you prefer more animations? Do you prefer when I'm doing the green screen stuff and I'm doing hand wavy things? Or what do you prefer? These videos are for you, they're not for my benefit. So please do let me know what you want. All right, check out these playlists and also check out my Pokemon videos if you wish. All right, stay safe. I'll see you soon.